Hello everybody. Today we would be talking about edge triggered D flip flops. In our previous lecture, we have studied what is a basic memory element, and we have seen that if we put a feedback loop in around any circuit, then that particular circuit can work like a memory element. So we started with inverter, and then we have seen that if we want to set the storage value to 0 or 1, then we can create a set reset or RS latch. So in this RS latch, the beauty was that if we have to set the stored value to 0, we have to make set as 0, set as 1 and reset as 0. Similarly, if I want to store a value 0, then we have to make reset as 1 and set as 0. So this particular combination gives us a good powerful mechanism so that we can store either 0 or 1 inside a memory element. And this memory element is created from nothing else but our basic gates like AND, OR and NOT. Now this set and reset, although it's a good powerful feature, but if I want to set something, let's say I want to set something which is variable, so I want to either set 0 or set 1. So this combination of set and reset, what should be the value? So there has to be some additional circuitry, additional number of gates that need to be employed so that only either set or reset is 1. To avoid this kind of additional circuitry, so one of the flip flop, one of the latch which we have studied in our previous lecture performs excellently. So for this particular work, this latch is called D latch or delay latch. D is sometimes used for delay also, because whatever is the input, that is given as the output here. Now in delay latch, whatever we would like to give, so let's say there is a signal X, and this X can be given as an input to my D latch, then the output would be same as whatever is written in the D. If D is 0, then output would be 0. If D is 1, input is 1, then output would also be 1. But where is the storage element? So the storage element can be created if we put a controlled or basically a control input. So if this control input is 0, then whatever was stored in latch, that will remain stored. If control input is 1, then it works like a transparent logic. So whatever is the input, that would be the output. So essentially, if I want to store anything inside a latch, particularly D latch, then I will make this control input as 0, and then whatever was stored, it will remain stored. And whenever I want to store anything, I will make this control input as 1. So this gives us a very good mechanism that if I have any variable or any particular signal and I want to store whatever is the value inside that signal I want to store in a memory element, then I can use D latch. The only problem with the D latch is that we have to make sure that whatever we want to store, or whenever this control input is 1, then the value whatever we want to store is there at the input. Because if my control input is 1, whatever is at the input D, it would be transparently reflected at output Q. Because it would be transparently reflected at output Q, so that means if this D is changing, my input is changing, it is fluctuating, my output will also fluctuate. Other thing, I have to make sure that whatever I want to store is correct at this particular time. So this is also, that's why this particular latches are also called level triggered. So whatever is the level, if the level is high and it would trigger at this high level, then whatever is the input, that will be stored. Now because this level, or when my control input is 1, that gives significant amount of time to change in my input. That's why these latches may not be a very good component to do synchronization or to store the value for definite amount of time. Yeah, value can be stored for definite amount of time, because this 0, whenever control input is 0, that we can control. But the value, when we cannot make sure that my D would be stable, my input would be stable during when it is 1, when control is 1. So if I want to have storage element which can store the value at precise time, that's why we would require something which is additional. Okay, so what is this precise time? For this, I'll take a small detour and I'll try to explain one of the very important synchronization signal, that's called clock. In most of the digital circuits, this clock signal or a clock wire is a very one of the very important signals, because it synchronizes. What do we mean by synchronizes? So particularly in synchronous sequential circuits, whenever all the inputs would change at same time, all the outputs will also be reflected at the same time, so they would be received at same time. So that means when all the components, so you may have various combinational logic, adder, multiplier, multiplexers, all of them, they would be synchronized with one signal, that's called clock signal. So this synchronizing signal clock is essentially the basis of synchronous sequential circuits. Now, why it is important? Because many a times we would like to divide our work into smaller steps. Each of this step, if we make sure that each of this step can be done in some definitive time, then things get easier for analysis, things get easier for designing. Okay, so that is why this clock signal is used in almost all kind of digital circuits. You can take an example also. For example, when you go to market and try to buy a computer, so you will see what is the clock frequency of this processor. Try to remember that what is the clock frequency of your processor which is there in your laptop. So it must be somewhere around 2.4 gigahertz, 2.8 gigahertz, or maybe 3.2 gigahertz. What does that mean? It means that your processor is driven by a clock which is running at the frequency of 3.2 gigahertz. That means in 1 second there would be 3.2 into 10 is to power 9 clock periods. So what does this signify? This signify that the smallest step in or smallest work that can be done in your computer would be done in this 1 clock period. So essentially a clock signal is characterized by these two features. One is called time period, another is duty cycle. So time period is after how much time the clock signal will repeat itself. 1 by t is frequency, and usually the frequency would be it could be in kilohertz, megahertz, gigahertz. So in last 20, 30 years, 40 years, this clock frequency used to be one matrix of performance. For example, some 40 years back, 50 years, 45 years back, when first processor came, it used to run on 1 megahertz. Now slowly these processors have started working on a couple of gigahertz. So this fast paced transition, this was because now we are getting faster, and that's why these clock frequencies are shrinking. Clock period is shrinking, clock frequencies are increasing day by day. So a clock period is one characteristic of your clock signal, and now clock signal would be essentially it would be high for some time and then low for some time, and then again high for some time and low for some time. And one thing which would be there in most of the in the clock period of at least in computers, that it would be same. So clock period is going to be same, and it would be high for same amount of time, it would be low for same amount of time. Because it is high for same amount of time, that's why we can also have another signifying characteristic of a clock signal, that's called duty cycle. So we can call it a pulse. So whatever is the size of pulse width, the amount of time for this pulse or the clock signal is high, divide by total time period, we can say that is the duty cycle. So ideally duty cycle could be 50%, that means 50% it is high, 50% it is low. But in different kind of circuits it could be anything. It could be duty cycle could be 10%, it could be 80%, it could be 90%. 50% gives some ideal characteristics, and it also gives some advantage which we may talk some time later during the course. So these are the two important characteristics. The other characteristic is at what time should we synchronize. So there are two interesting times here. One we say a rising edge, the other we say falling edge. Rising edge means when clock will rise from 0 to 1. That's called rising edge, because clock was initially 0, then it is 1, and this edge is a rising edge. You see that in the right direction we are increasing in the time. So initially at some time it was 0, then it has increased to 1, so this is called rising edge. It's also called positive edge. And then the other is negative edge, when our clock will go from 1 to 0. So with time from 1 to 0, this is the other transition. So essentially there are two transitions. Each of the transition can act as a synchronization point, rising edge and falling edge. Now let's get back to this kind of a storage element which work on some precise synchronization points. These storage elements, memory elements, which can store the input at precise synchronization point or precise transition points, are called flip-flop. They are also called so they will only change the output during the transition of clock period. They will not otherwise change their output. Now output will change, and we have seen that there are two transitions. One is positive edge or a rising edge. So let's say now let's take an example of a flip flop, which is we are saying it's like a D latch, but it's a D flip flop. Now the difference between the symbol of a D flip flop and D latch is, additionally you see this arrow. This additional arrow represents that this particular circuit is sensitive to transition. So that means whenever this clock will transition from 0 to 1, that means there would be a rising edge or there is a positive edge, then this output will change, otherwise output will not change. So my input can be anything in between, but when there would be a rising edge of the clock, then only there is a possibility that Q will change, otherwise Q will not change. Similarly, there could be other transition which could be negative edge or falling edge. So for negative edge or falling edge, we put a circle on the clock signal. So this arrow will still be there. This arrow signifies the edge triggered flip flop. This circle means negative edge. Oh, okay. So this, if we have a circle here and we have an arrow like this, that means it's a negative edge triggered flip flop. So what is the meaning of this whole sentence? Negative edge triggered. So that means this flip flop will trigger only when the clock will have a negative edge. In other words, the output will change only if clock has a negative edge. So at the negative edge, it will probably see the inputs, and based on that the output will change. There could be various type of flip flops. This D flip flop is one of the example. There could be JK flip flop, RS flip flop, T flip flop. So those flip flops we'll study in forthcoming lectures. So today we'll focus on the basic property of a flip flop, and so we take the simplest one, D flip flop or a delay flip flop. Now, a delay flip flop is represented by a characteristic equation that the next state is equal to D. Now, you see there is no control signal. So, at what time Q plus or next state would be equal to D? When there is a positive edge. So, you see an arrow here, that means the clock transition, and because there is no circle here, so that essentially means whenever clock will be rising edge, whenever it would be positive edge of the clock, then my Q plus would be equal to D. Otherwise, it will remain whatever is the previous value of Q. So only during this positive transition, the output can change, and the output would be equal to D. So that's what we call a characteristic equation of this particular flip flop. So two important things. One, D would be passed to Q plus or the output only at the positive edge of the clock. The second thing, my output will not change during the rest of the clock period. So to understand this, let's take example. So let's say this is my clock signal, and sometime to represent that my clock signal, my this flip flop is positive edge triggered, so I have put an additional arrow. So this additional arrow signifies that at this moment of time, whatever is the D, that will become Q. So because D was 0, Q has become 0. At the during this period, from this clock time to next rising edge, my D has changed multiple times, but it doesn't matter. It does not affect my output at all. Now, when the next positive edge has come, at that time again we sample D, or we'll see what is the input at D. Now, because D was high at that time, so my output would remain 1 till next positive edge, and the next positive edge again we have sampled. What is the input of D? What is the value of D? This was 0, so it remained 0 for during whole one clock period. So similarly for all other places, but here this also you see that now during this positive edge my input was 0. Here because D was 0, the output became 0. Before the next positive edge came, the output has again become input has become 1, but it came 0. At the time of sample, it was again 0. So output didn't change. Output will not change according to the transitions, but at transitions of the input only, output will change whenever there is a transition in the clock period. You can say, or you can question, what is the utility of such a circuit which is so constrained? This constraint that my output can change only at a fixed time is putting some constraint on the input, but it is also making sure that my output will also not change for one clock period. What does it mean? It means that these output can also be given as an input to some other signal, to some other circuit. So let's take an example of an addition. We implement 32-bit adder, and we implement it using ripple carry adder. So and let us say the input which is coming to my ripple carry adder is coming from a flip flop. So which will make sure that the input to my adder will not change for during that whole one clock period. Now, what should be the size of clock period? So this gives me an advantage, because my input will not change for one clock period. Then this will give me an advantage, a clear advantage, that my circuit will not go wrong because my inputs are stable. Because they are coming from a flip flop, there is no chance that my input will change before output has come. Now let us say, because of ripple carry adder, and it's a 16-bit adder, let's say the delay of this whole 16-bit adder is 35 nanoseconds or 35 units. Now what if I make sure that the clock period is more than 35 nanosecond or 35 units? That means my input will not change for 35 units. Now let's consider further that the output of this adder is further used as an input to another D flip flop, which means that the output of this adder can keep on changing during this whole 35 units of time, and it keeps on changing. We have seen. So when we did this adder assignment, we did this Verilog code, we could see that the output keep on fluctuating. Only at the end of 35 units of time, we make sure it is sure that output will not further change. So that means this fluctuation can keep on happening, but whatever is the output of the adder at 35 units of time, we can sample it at correct time. So this gives us some additional constraint to our circuit also, that if my circuit has certain delay, I can set my clock period accordingly. Or in other words, if my clock period is fixed, then I can make my circuit accordingly, that my circuit should stabilize its output before the change of clock period. So this gives us an additional a powerful mechanism to design very complex circuits. You can see your microprocessors can run very complex softwares accurately. There is very less chance, there is almost negligible chance that your system will go wrong. It's precisely because it is defined that within one clock period what work can be done. Okay, so now how can we design, how we can implement using our basic gates this kind of a D flip flop? Design can be done using two D latches. So if we have two D latches, one is gated with a clock signal which is inverted, the other which is gated with a clock signal, then we can design this rising edge triggered flip flop. So what would happen, because the clock is inverted, now whenever clock is negative or clock is 0, when the clock signal is 0, at that time whatever was the D value would be given as the output of first D latch. Now the output has gone to first D latch when clock was 0. Then there is a clock transition. At the time of clock transition, here after that clock transition, this has become 1. This is the positive edge. From 0 it has become 1. And at the time of 1, whatever was stored in this output of first latch can be given as the output. So the overall mechanism is such that my D value, this input value, can go to final output only during the rising edge. Otherwise, whatever is this D value will never be transmitted here, will never be stored here or given as the output. So you can consider all other cases. For example, whenever this is 1, this particular clock is 1, then this delay latch will not be active, so this Q will not change. Similarly, when this is 1, this is 0, then this particular delay latch would not be active, so this Q will not go here. So during the rest of the stable periods, input will not go to output. Only during the rising edge, the input D would be given as the given as the output Q. Correct. So similarly, if we want to design negative edge triggered D flip flop, then the clock would be connected here, and the negative clock, so the inverter would be connected to this particular gated input. So because I would also like to assert that this is one of the implementation. This is only a one implementation of D flip flop. Now, since these are all fundamental circuits, they are used almost everywhere, almost in different combinations, different places in digital circuits. So they are designed. There's a lot of focus on designing such kind of flip flops. So they are also designed directly using transistors, using CMOS transistor, PMOS, NMOS, or different type of transistors, and there is a optimization within. So this is one of the simplest implementation which is using gates, but they can also be directly implemented using transistors. Or there could be other mechanisms also to implement edge triggered D flip flop. So, but one thing from this analysis or this kind of a circuit, we understand that ideally the behavior of a D latch or D flip flop is that during the positive edge, whatever is the value of D would go to Q, but in a practical scenario, there is some delay of this D latch, there is some delay of this D latch. So there has to be some other timing constraint which we have to adhere. These timing constraints are represented using this diagram. Now let us say this is my clock signal and this is my active edge, or this is the edge at that time we would be taking the input and giving it to output. So we have to make things work perfectly, we have to make sure that D or the input will not change at least setup time before this rising edge and at least hold time before this rising edge. Now to make it towards the ideal arrangement, the setup time has to be minimum, hold time has to be minimum, but yes, practically there would be non-zero values. So let's look at in this circuit, whenever this circuit was this clock was negative or clock was 0, that means this gated input was 1. So that means whenever it was 1, at least sometime before that, whatever should be the value of D will go in the output of first latch. Similarly, because it was available at some time before the latch, and whenever this particular gated input become 1, then only this can go and transfer to the Q. So essentially there has to be some setup time involved, and during this window my input should not change to make sure that the output is correct. The other information which is there, so this is one restriction which is on the setup time and hold time. There is one additional additional timing thing which we have to understand, that whenever input will change, so whenever there is a positive edge, so after this positive edge there would be certain time after which the output would be reflected onto Q, or at the output of my D flip flop. So that would, I can call, latency of my flip flop. So the latency would be calculated from the rising edge or the active edge, but setup time again would be calculated with reference to my active edge. So setup time would be the time when my input should be stable, and whole time after this clock edge, active edge of the clock, for how much time my input has to be stable. So my input can toggle anywhere here or anywhere here, it doesn't matter, but during the setup and hold time window, input should not change. That's a restriction which will make sure that my circuit is will function correctly, and these are also called design constraints. So whenever we are designing any circuit, we keep these timing constraint in front of us. So with this we conclude today's lecture. So in summary, in today's lecture we have seen how an edge triggered flip flop can be designed, how this fundamental circuit help us in synchronizing different signals, and how this synchronization is made, how it is internally implemented. All of these things we have studied in today's lecture, and in our next lecture we will see other implementation, other different type of flip flops which are possible, and their applications. Thank you very much.